All right, we're here for the second air resistance free response problem. It's in the packet. This one says, hey, a car of mass m, initially at rest at time 0, is being driven to the right along a straight horizontal road with the engine causing a constant force F0 to be applied. While it's moving, the car encounters a resistance force equal to negative kV, where v is the velocity of the car and k is a positive constant. You say, yeah, that's my resistive force. It depends on the velocity, right? And the direction negative kV, it's going to go opposite the velocity. It's going to be pushing against the motion as it goes. Okay, this dot represents the center of mass of the car. On the figure, draw and label vectors to represent all of the forces acting on the car as it moves the velocity v to the right. So I'm going to go ahead and say here, we're doing a force diagram. Look, that's my car, right? And so you say, okay, I want to draw all of my my forces on there. Draw and label. So you say, all right, ranged forces, there'll be a gravitational force on that car. Contact forces, what's touching it? Well, basically the road surface and this air resistance. And so you say, well, the road, are they pressed together? Yes, they are. So there's a normal force that would push upward. And then you say, are they trying to slide past each other? No. Technically, we know that as the tires are turning, it's like they're going to try to slip on the ground, and static friction fights against that, and that's what drives you forward. Well, that's happening because the engine is turning the axles and such. That's that force that they're talking about, that constant force F0 being applied by the engine. It's really technically that F0 is technically that friction with the ground. That static friction keeping you from slipping, driving you forward, that giving the car that traction. That's what we're talking about there. Okay, and then there's this resistance force, kV, going to the left. All right, that's my force diagram as it's driving along. Okay, part B. They'd like to know the horizontal acceleration in terms of these variables k, v, F0, and m. And so you say, well, the way we're going to get acceleration is we're going to use the most important formula in physics. We're going to use sigma F equals ma. And so you say, well, let's do the horizontal axis is the one we care about here. That's where the motion's happening. That's where there's a term with velocity involved, right? And we're going to be able to get acceleration. We're not accelerating in this axis. It's just the horizontal axis we want to look at. So I do my forces. Again, we're calling to the right positive. Going to call the right the positive direction. And so I'll have that F0. Now be careful here. When we do this, we do forces right minus forces left. That minus is to show direction. But you see that negative is also to show direction. I don't want to do minus a minus. That would make us add. We don't want to do that. So it's just minus kV. Be careful about the signs. Is ma. They want acceleration in terms of those variables. You say, look, kv F0 m, kv F0 m. Look at that. I just got to get the a by itself, and I'll be done. And so I just divide through by m. F0 minus kv over m is my acceleration. And that's what they wanted. Acceleration in terms of those variables. Part C. They say, can you derive the equation expressing the velocity of the car as a function of time t in terms of da-da-da? So they want v as a function of time. All right. And so you say, well, yeah, I can do that. All right, in terms of k, F0, and m, we'll see. So what I'm going to do is I'm going to go ahead and I want velocity as a function of time. And so I'm going to do F equals ma again, right? Basically, I'm going to do the same steps here. The difference is I need velocity as a function of time. There's no time in this equation. So what I'm going to do, the trick is I'm going to swap out the acceleration for dv dt. So I've got F0 minus kv. I'm going to go ahead and split that m up for my own secret purposes. Where it says a, I'm substituting in dv dt. Now I'm going to have an equation that's going to have v and time in that equation, which is what I want. Now I want to have an equation where I can put in t. I've got dt. All right, that's not cool. So this guy, again, is a differential equation. I've got v and its derivative in the same expression. That's a differential equation. Solving involves this special technique. We're going to use separation of variables. Okay, we're going to solve by separation of variables. Sep of theirs. Right, anyway. And so I'm going to get my v's and dv's on one side and my t's and dt's on the other. The way I like to do it is I like to get the variable with a coefficient of +1 first. So I'm going to multiply through by m, move the m to the other side. I don't know why I split that up. That was silly. Yeah, we're going to get a coefficient of 1 on that v. So to get a coefficient of 1, I'm going to multiply through all the terms by negative m over k, right? And that'll give me a coefficient of +1 for that v. Multiply this by negative m over k. The m's will cancel, and I'll end up with negative f naught over k. Multiply by negative m over k. It'll look like this. Okay, you okay with that? I multiply by negative, and I move this term to the front. Okay. Now, the trick is I'm going to treat this chunk like it's one thing to move around, okay? I'm also going to it looks like, it's going to look as if I'm treating the dv and the dt like they're two variables being divided by each other. That's not what's going on here. Yeah, don't sweat it. Multiply through by dt, both terms, and I'm going to move, is what it looks like I'm doing. And I'm going to, okay. So I'm going to move the dt to this side. I'm going to move the negative k over, I multiply by negative k over m. Okay, so I'm going to end up with just dv there, right? Okay, I would just have a dv left here now, right? Multiply by negative k over m dt. Now what I'm going to do is I'm going to take this chunk, I'm going to divide both sides by this whole chunk in parentheses. So I have a 1 over that chunk. And that will separate my variables. So I've got just t's or dt's on this side, and all my v's and dv's are on this side. All right, at this point, we're going to integrate both sides. I'm going to integrate with respect to time, integrate with respect to velocity. I'm trying to find a velocity as a function of time. Any future time t I can plug in and find future at any future v. So I want this to go from the start, from time 0, to any future t. And when I get velocity from the velocity at the start, well, this thing started at rest. So my starting velocity is going to be 0 to any future velocity v. All right. All right. Doing this integral really quickly. K and m are constants. So this is just going to be negative k over mt, evaluated from 0 to t. Over here, this is going to be this 1 over variable minus a constant. This is going to be the natural log of this variable minus constant absolute value. And I'm going to evaluate that from 0 to v. Alrighty. Whoops. Evaluated from 0 to v. Okay, this one's pretty straightforward. When we do this evaluation, we plug in the final value minus what we get, we plug in the initial value. So minus value is just negative k over mt. Minus when I put a 0 in, well, that's just 0. That minus 0 is just that. Okay, on the other side, put in the final value. That would be the natural log of, put the v in for v, that's just v, minus f naught over k, minus when I put the 0 in for v. Put the 0 in for v, that'll just be the natural log of negative f naught over k. All right. Yep. Okay, now that I've done that, I've got two logarithms with the same base. This is base E, it's natural log. When you have a subtraction of two logarithms with the same base, you can turn it into a division. It's like this weird property of logarithms. So this will be just natural log of v minus f naught over k. And I'm subtracting this, so this will be in the denominator, minus f naught over k. All right, and so this negative k over mt. Okay, so my last step here. Not my last step, but what I want to do is I want to now take this logarithm and make it not a logarithm anymore. I want to exponentiate it. This is log base e of this equals this. When you have a logarithm, my base e to this power equals this. So I'm going to jam that over here. Look at me, squeezing it over here, and this is fine. I'm going to have, when I take the unlogify it, exponentiate it, I'm going to get that v minus f naught over k over negative f naught over k equal to e to this power e to the negative k over mt. Okay, you don't mind that I flip-flop sides, do you? Thanks. Okay, yeah. All right, so I'm going to go ahead and I'm going to multiply both sides by this. I'm going to move this up top here, and then I'm going to add this over. See, that's f naught over k, f naught over k. Look at that. So I'm going to end up with, I'm going to do both steps. I'm going to multiply through by this denominator, and then I'm going to add this f naught over k to both sides. I'll end up with v is f naught over k. That's the one that I added over, right? And then I had multiplied by this, that would have been a minus f naught over k times e to the minus k over mt. All right. I could factor f naught over k out of this. Now I just have 1 minus e to the minus k over mt. Okay, that's my exponent there on e. All right, that's what I've got. Okay. So that is my velocity as a function of time equation that I was trying to get. I'm going to point out to you really quickly here, hey, this bit in parentheses here, when time is 0, I'm going to look at it from time 0 and then look at it as time approaches infinity, that's a infinity sign. When time is 0, put a 0 in for t, what would this expression in the brackets be? E to the 0 is 1, 1 minus 1 is 0. So this is going to start at 0, and it's going to approach. As time heads to infinity, e to the minus infinity, that would be 0. 1 minus 0 is 1. So the bit in brackets is going to be a decimal that goes from 0 to 1. It's like it's a percentage of this thing in front. You know what that is? That's the terminal velocity for this object. That's the final velocity. We're going to start from 0 and head up to 100% of terminal velocity as time approaches infinite, right? So this is what that v terminal is. It's going to be equal to f naught over k, as it turns out. Okay, so that's that expression. All right, and interpreting it just a little bit. Okay, so getting back to this, they want an expression for velocity as a function of time in terms of k, f naught, and m. Look at my variables here. I've got k, f naught, k, m. V is a function of t. E is not a variable. This is Euler's constant. It's a value 2.7, blah, 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 blah. Okay, good enough. So that's it. Okay, can we graph this thing? You say, yeah, but I don't even have, I could try to graph this equation, but I don't have to look at that, okay? I can sketch a graph of velocity as a function of time just knowing what's happening in the problem. What's the starting velocity? Well, it's initially at rest. So I know my graph has to start from here, okay? I'm going in what I'm going to call the positive direction to the right. So my graph's going to be heading upward. I'm starting from a velocity of 0. I'm getting faster and faster, right, as it goes up. But I recognize that as I get faster, this force pushing against me is going to get bigger. So the total force to the right, F naught's a constant, but my total force is going to be getting smaller. As this arrow gets bigger and bigger and bigger, it's going to subtract off more and more from the velocity. So my total force gets smaller, that's pushing me right, and so my acceleration to the right gets smaller. How does acceleration show up on a VT graph? It's the slope. I'm going to start with a big acceleration when I don't have any air resistance at the start, just this F naught pushing. But then it's going to get less, smaller acceleration, so a smaller slope. Eventually, as time approaches infinite, this velocity will be approaching terminal, and this force will be approximately the same size as this. And so I'll get a total force of 0, which means an acceleration of 0, which means a horizontal slope on the VT graph. So this is going to be one of the is asymptotically approaching the terminal velocity. We also know that terminal velocity, we figured out here that that terminal velocity was going to be F naught over K. There is an easier way to find terminal velocity than what we just went through. That would be to take this equation and put in a 0 for acceleration. When I'm at terminal velocity, that's when the forces balance out, right? And so the total acceleration would be 0. If I did that, if I made that 0, this V would be V terminal. And so that would have F naught minus M times V terminal equals 0, right? Oh, look, V terminal is what? F naught over M. F naught over M. F naught over K. What the? This is a K. This is a K. It's a K. Oh my gosh, look at what I did. Yeah, F naught over K, right? The M went away when I multiplied by 0. Sorry. F naught over K. And you say, hey, that's what we had here as our coefficient F naught over K. That is the terminal velocity. Okay. Last part. On the axis below, sketch a graph of the car's acceleration, A, as a function of time t, label any important values on the vertical axis. All right. So we know that our acceleration at the start, starting acceleration, I'd have the starting velocity. The starting velocity was 0. So my starting acceleration is F naught over M. All right. Okay. At the start, I just have this big force pushing the positive direction. F naught is the total force. F divided by M would be my acceleration. So I'm going to start with a positive acceleration. I'll start way up here. This will be F naught over M. Okay, is my starting value. As time goes on, I get faster. This is going to be subtracting more and more off from that. And so my total force is going to be approaching 0. So my acceleration is going to be approaching 0. So it will be decreasing. And eventually, as that force balances out, my acceleration approaches 0. But it will take an infinite amount of time because at the end, as this velocity approaches terminal, right? As this gets close to terminal, then the acceleration is really small, right? As these forces are just about to balance out, kV and F naught about to balance, this difference will be approaching 0. And so the acceleration approaches 0. So how fast can that velocity change now? Going to take infinite amount of time for it to tick over that last bit of velocity to get to terminal. So it's never quite going to get to terminal. It's asymptotic at 0. That's what we're looking at. Okay. Hey, that was just conceptually getting that graph and doing a quick terminal velocity, a little calculation here, right? To find that initial acceleration, putting in a 0 for velocity gave me the initial acceleration. Okay, well, could we actually find the function? They didn't ask you to find the function A as a function of t, but we could do it because we already found the velocity as a function of time here, right? We say, what's the relationship between velocity and acceleration? Acceleration is the derivative. Could we take the derivative of this? It'll be a little easier if we take the derivative of this equation. Okay, so I'm going to go back one step and take the derivative. If we did that, check it out, right? You would say acceleration is dv dt. So acceleration is going to be the derivative. So I'm going to take the d dt of that expression, F naught over K minus F naught over K e to the minus K over mt. You say, now look, these are terms addition, right? And we take the derivative. The sum rule says the derivative of the sum is the sum of the derivatives. What's the derivative of a constant term? F naught and K are constants. That's just going to be 0. It's just going to drop. So I just want to take the derivative of this thing. Constant. We take the derivative of an exponential like this, you know that the derivative is just going to be e to the minus k over mt with a minus k over m kicked out in front because of chain rule. So I'm just going to kick a negative k over m out in front. The k on top and the k on the bottom will cancel. The negative will cancel. I'll end up with F naught over m e to the minus k over mt. And that is my derivative. So that's my acceleration. F naught over, and hey. You know what we said the starting acceleration should be? That would be the acceleration when I put a 0 in for t. E to the 0 is 1. Look, F naught over m. F naught over m, that's what we got. So it matches. And this is again an exponential decay. You say, if I take a look at this part here, time is 0, heading to time approaching infinite. You said when time is 0, e to the 0 is 1. And as this heads to infinity, this value, when I put an infinite in, e to the minus infinity, it will be 0. This is going to be a percentage of that starting acceleration that I have. My starting acceleration was my biggest acceleration. This tells me what percentage of it I'm at as time goes by. That's what this bit does. And that's it. Okay, that is that's it for that second AP true response problem. Yeah, hopefully that's pretty good. All right. Oh, right. Yeah, and again, all this, the integral stuff and I mean, once you have the velocity equation, you should be able to find the acceleration. Just take a derivative. But the integral stuff, don't sweat it yet. If it's the fall semester, in the spring, you'll be expected to be able to do it then. But you will have seen this in your AP Calculus course by that time. And so everything will be fine. It'll all be good. All right.